Marepalli. I welcome Dr. Mahua Chakravarti. I welcome Dr. Suresh Kumar and all my friends, colleagues, participants who are viewing this webinar online. Today, the seminar topic is ISSE 75 revision 2015. Dr. Suresh Kumar is a person who has studied it well. For information to all of you that these codes are regularly gets updated. So our team want to highlight the things which are required for upgradation in future or currently whenever their codes are revised, there may be shortcomings because of many reasons which we don't know. Normally codes gets upgraded at regular interval in Europe countries, but in our country also with help of Dr. BIS Director Sanjay Pant, codes are getting revised, upgraded based on experience, feedbacks, expertise, material availability, new things, research, and gets upgraded. And hope after this seminar, whatever recommendation comes, ISSE will try to send it to BIS for incorporating whatever is best possible. Now, I take my privilege to introduce Dr. Prasad Marepalli. First of all, he is a very close friend of mine. I am very happy that we are together today. He is a civil engineer. He started his career as an academician. Then after a few years, he joined his PhD at IIT Chennai, Madras. And after his PhD, he joined a company which is responsible US company, consultancy company, where 100 buildings of Florida has been designed during his tenure, and he is responsible in all design matters of those buildings. Thereafter, he went Dubai, and he was involved in very big company where most of high-rise buildings were reviewed by him. He was also involved in construction. He has all-round experience. And one thing I will like to specify about him, that whatever he do, whether work is small or big, but he will definitely give justice to that. That is his beauty, what I personally know about him. Even if a small thing is there, he will take proper interest and do the justice to that work. Currently, he is in Loda Group as a senior vice president, and he is involved in many strategic things, taking decisions, not only structural design matters. He is helping all team, coordinating structural engineers, architectures, and trying to find out optimum solutions. And is one of the best experts whom I know personally with all-round experience. I can say about him about 1 hour, but time is very short. Now, Dr. Mahua Chakravarti. She is 81 graduate from BJTI, Mumbai. Also my classmate, I was also with her only. Then she worked with TCS. Thereafter again, she joined BJTI for ME structure. Then she went to IIT Bombay for PhD, one of the expert in dynamics. She in academics for 35 and more years. She taught many people, for many students for ME dissertation, and continuously for dynamics. She is one of the experts. She was High-Rise Committee of Mumbai. Then she is currently New Bombay High-Rise Committee member and also member of committee which declares building unsafe in New Bombay. With this, I request you to take up further. Hello. Hello.
Yes, sir. Thanks. Now I invite Mr. Hemant Bodalkar to say a few words about ISSC.
Hello, good morning to all. On behalf of Indian Society of Structural Engineers and RWDI, I welcome you all to this webinar on a very interesting subject. I will just speak few words about ISSE. Indian Society of Structural Engineers has been formed about 22 years back by our visionary late Mr. R.L. Nene, and we are providing this as a platform for knowledge sharing. And we invite different experts in the field of structural engineering and other fields of civil engineering to share their experience and knowledge with the fraternity of civil engineering. And today is another attempt what we are making with Dr. Suresh Kumar. He is an expert, international expert on wind engineering, as all you know. And if you remember, we had conducted one workshop also with Dr. Suresh Kumar, and we have published a booklet on the similar subject. So those who are definitely interested, they can of course get the publication from ISSE. And we also maintain our website wherein we have all the technical references, our bulletins. We generally publish the technical magazine bulletin every quarterly, and then we try to share the experience of our fraternity members, the case studies and different technical subjects. Those are being covered in our bulletin. So I request all the fraternity members, the experts in the field of civil engineering, you can share your experience with us in a form of some article, some write-up, whatever may be. It is related to design, it is related to construction, related to site management, or any extraordinary structure what you have designed. So please share the data with us so that we can publish it in our bulletin also. We generally conduct webinars and seminars all the time. Due to the pandemic, there is no other option but to go online. So that's why we are having this type of webinars nowadays through ISSE as well. And you can visit our website all the time. It is issc.org.in. We have all the information there. And I appeal to all civil engineering fraternity, those who are not our members, kindly become our members and strengthen the hands of ISSE so that we can take this knowledge sharing platform forward. Thank you very much.
Thank you, sir. So now I invite Dr. Prasad for his introduction talk about Dr. Suresh.
Thank you, Mr. Wadalkar and Shantilalji. Hello all, good morning. Hope everyone is staying safe in these pandemic times. Thank you for joining us in the spirit of learning and discussion. Pleasure to be a part of the ISSC webinar on wind loading on tall buildings today. I first learned the importance of wind codes in early 2000 when I started designing high-rise buildings in Florida for hurricane wind loads. At that time, I was at Bangalore working for an American consulting firm. Dr. Suresh Kumar is well-versed and highly regarded professional in the area of wind engineering. Our relationship extends back to year 2001 when he was still at RWDA office at Canada, and today as head of structural design at Lodha Developers. I asked RWDA to conduct the wind tunnel tests of our tall buildings in Mumbai at their Trivandrum facility in compliance with the provisions of IS Indian Code standards. It is worth mentioning here that Dr. Suresh Kumar played a key role in bringing and setting up this world-class wind tunnel test facility in India. As a global wind engineering consultant at RWDA, he is very active in professional bodies around the world and also in India. We very frequently discuss on wind, the response of our tall buildings, wind-induced loads, and the complexities associated. I am happy that this kind of discussion with him is going to happen online today now. When I look at the industry in last 2 decades, I see Indian engineers are now well-versed with not only the Indian codes, but with the international codes, American, Australian, European, just to name a few. This is because they work on both national and international projects at the same time with the same ease and possibly being in the same office. The second revision to IS 875 came in 1987 and the third revision in 2015. It is after the year 2000, the high-rise construction started in India. We need to see the in the country and vis-a-vis the progress and the changes that were affected to the code. So it is after the year 2000, the high-rise construction started in India and buildings started becoming more slender and more flexible. For the benefit of students and for those who are not in tall building design practice, I want to mention here that wind loads on buildings depends not only on the geometry, but also on stiffness, mass, and damping of the building. Rigid buildings attract less wind compared to flexible buildings. The more flexible the building is, the more wind load it attracts. Serviceability criteria, when I say that, means drifts and accelerations also need to be checked. Wind codes account for the fluctuations in the approaching flow in along wind direction by use of gust loading factors. The 1987 version of the code considered the flexibility in along wind direction, but under the action of the wind, tall buildings oscillate simultaneously in the along wind, across wind, and torsional directions. The 2015 revision to the code accounted for this flexibility in across wind direction, first time. When this third edition to IS 875 was released, engineers were first happy to see the crosswind and serviceability provisions, but soon they realized the loads being estimated to be on higher side for certain practical configurations. This understanding was well established by early 2017. And we at Lodha have experienced the same on our projects. When we apply this across wind simultaneously with the wind, along wind, then the resulting loads turned impractical for design in few cases. There were no provisions for considering the torsional wind effects in the present code. Hence, today's topic of wind loads is of interest to all of us, to all of us as design professionals engaged in tall buildings. So, Dr. Suresh and Shantilalji, thank you for having me as the moderator for this webinar today. I see the list of attendees growing very fast. I'm happy to note that there are several students who are online in the spirit of learning today. Dr. Suresh will deliver the presentation for about 45 minutes. Subsequently, he will answer to some of our questions. When testing your questions, I suggest let the questions be related to this webinar topic, wind code provisions for tall buildings, not on the wind tunnel procedures. If we ask questions to Dr. Suresh on wind tunnel procedures, he will take a few hours. So let us stay to the webinar topic, wind code provisions on tall buildings. Now I ask Dr. Suresh Kumar to start his presentation.
Thank you, Dr. Prasad, for the kind introduction and introducing the topic as well, which is very clear, so I don't have to explain more on the topic. And welcome and good morning to all of you who are attending today. And I need to thank ISSC team especially for conducting this. I think there is a great team behind it. Hemant Wadalkar, Mr. Ranganath, Dr. Mahua, and Mr. Shandalal Jain. They all agreed to this idea. And also thanks to RWDI team. We have a lot of people behind this arrangement as well. And before I move on to the topic, I hereby acknowledge really the contributions of the code writers. Even though I'm trying to probably comment on some of those provisions, but I really thank them for their contributions. The only thing that I'm trying to say is that we can betterment of the code, we have to do the amendments. And that is the whole point that I'm bringing it here. And as Prasad already clearly said, it is about tall buildings. I'm not going to talk about low-rise buildings. So here, I don't want to get into a debate on what is meant by tall buildings, but at least I want to say that I'm more concentrated on height above 120 meters, aspect ratio above 5, and period above 5 seconds. So this is the type of buildings that I'm talking about today. You can see the outline here, what I am trying to talk today. First of all, the concepts. You need to understand how the code is built. So that is something very interesting, followed by key changes which happened in the new code. And then I move on to local peak pressure coefficients and how do we estimate cladding loads, followed by structural loads, where the most important topics will be addressed, which is a long wind and a crosswind loading, followed by some suggestions for torsional loading. How do we estimate torsional loading, which we can amend in the new provision. And then getting into some interesting topics where load combinations and some miscellaneous topics I'm going to be talking towards the end with some few conclusions. So let us start with all your permission. So first of all, wind loading concepts. The code is built based on this particular concept. You can see the concept. How do you assess wind loading on any tall building? You need certain things to calculate wind loading on tall buildings. So this is the way the code is also built. You need wind speed and direction, which is particularly meteorological data coming out of airports. Then you need terrain roughness data in terms of oncoming flow field turbulence. So depending on whether you are in the Mumbai city middle or you are closer to the ocean, the terrain roughness is different, so which will alter the loading on your building. So that is also an important part, which is already addressed in the code, like Cat 1 to Cat 4 terrain conditions with turbulent densities and profiles and etc. The final aspect is the most crucial thing, which is local wind turbulence. And there are a number of different turbulence which is happening to the building, which is affecting the building. Not only just the oncoming flow field turbulence, there is something called wake turbulence. We'll talk a little bit more in the next few transparencies. We do have self-induced turbulence, which I'll be talking a bit more. Motion-induced turbulence, which is more like we call it inertial loading or resonant loading in terminology. Those terminologies have been utilized. So what is wake turbulence? You can look at some of these photos that I'm showing on the sides and as well as at the bottom. The cities are written. You know, nowadays no tall building is coming without another building besides it. So always there is cluster of buildings and the building is coming in between or towards the edge or whatever. You can see different cities and showing the cluster of buildings, then all of a sudden one building is coming in the middle. So the wake of all of these buildings, when wind is blowing, the wake of this wake turbulence is affecting your subjected building. That is something very important. The last photo which I am showing is the Mumbai city itself in one of the projects which we simulated in our tunnel. So look at these equations at the top. You can see the PD, which is very, I think you're all aware of these equations right from ISSE 875. PD or P bar D, which is mean reference pressure as well as design pressure with respect to the peak wind velocity. That includes wind speed, wind direction, and terrain height multiplication factor, which means earlier I said 3 factors. Out of 3 factors, the meteorology and the terrain roughness is already accounted in the PD or P bar D. So the local turbulence have to be accounted using some of these factors, which is CPE is the external pressure coefficient, and CFZ and G are supposed to be taking care of the wake turbulence. Those are factors which we already know. CFZ is nothing but the drag coefficient. G is the gust factor. So whether this is going to really take care of the wake turbulence, the answer is simply no. Because you know there are different scenarios happening in different cities. The code cannot really address the wake-induced turbulence. So we are missing that already in the code. Everybody has to remember that no code is going to take care of wake turbulence. So for wake turbulence, you have to go back to the tunnel, you have to do the test. There is no other way. Now the self-induced turbulence. What is meant by self-induced turbulence? You can see the shapes of the buildings coming. You can see Burj Khalifa getting tapered and with steps, a Shanghai Tower getting twisted. You see some of the low-rise structures with very, very complicated shapes. You have one of those tall towers in Vietnam that has lots of steps and etc. Then the last one is Statue of Unity, which also has a complicated shape. So the shape is doing a lot of things. So typically the code is addressing standard shapes. So that means you have squares and rectangles, triangles, some very familiar shapes that it is addressing, but structures are not happening that way nowadays. Everybody is coming with new designs. So you'll see a wide variety of shapes, and what these shapes are doing, we don't know. So whether this CFZ as well as G can take care of the self-induced turbulence, the answer is again no. Actually, it cannot. And unless otherwise, it is standard shapes. So we are missing that basically in the code. The code cannot address that. And that is another reason why we are doing the wind tunnel test. The last point is motion-induced turbulence. So in motion-induced turbulence, if you look at the equations, what you'll find is basically G is the gust factor, which is supposed to be taking care of the motion-induced turbulence. But G is not only just taking care of the motion-induced turbulence, it also takes care of the background turbulence. So you have two components there, background and resonance. And this is the motion-induced turbulence case. The background is basically the oncoming turbulence case, which is also taken care of through G. So essentially what you are doing in the code is basically you are calculating the mean load using CFZ, AZ into PD bar. That will give you the mean loading. And after calculating the mean loading, you are just multiplying with G to get your peak loading. So it is a very simple equation. And this equation has been widely used in most of the codes. We are not the only ones using this equation. You will see after a while, who else is using some of these equations. So this is just to give you an idea about how the code is being built, basically. So the conceptually three components. One is meteorology, second is profile, third is local turbulence. Now let us go into some of the discussion of key changes, what really happened in the new 2015 code. First of all, profiles. I have tried to plot the profiles in category wise. That means the first line is category 1 profile I'm plotting. I brought in Australian code as well as American code. So the Cat 2 is below. So you can see certain regions, you know, the Australian and Indian are coinciding. For instance, the Cat 1 where the turbulence is similar. Cat 2 also turbulence is similar, you can see. But then when it comes to mean, the ISSE is slightly higher than Australian code. So we don't know exactly what is the reason behind that, because I thought that we are closely following Australian code in some of these parameters, which you will see that many of the things which is right now in IS 875 2015 is coming from Australian code. So this difference, why this is different, I can't answer here. So this is something to be, we should be thinking at a later date when we are trying to amend this code again. So there is difference between the mean profiles between the codes. If you go to the Cat 3 and Cat 4, especially in Cat 4, you can see in Cat 4 peak velocities are very different. The IS code is much higher than the Australian code. It is very evident from this. But then you go to the mean profile, there is not much difference. Then you go to turbulence, there is some difference, but not a lot of difference. So why this is happening is again a question mark, because being our roughness length exactly the same as Australian code, because we use roughness length nowadays with Z knots, with the 0.002 to 2 meters. 2 meter we are using in the Cat 4 terrain. So this is something to be questioned, because this is going to directly affect our reference pressure, so which is very important. And now we also brought in cyclonic factors. I have given another webinar exclusively for cyclonic factors, so I'm not going to get into the details. So basically what we are saying is at the coastal region, we want to elevate the speed using another factor, which is K4. So they say that basically in post-cyclonic regions, you increase the speed by 30%, and in industrial structures, you increase it by 15%. Then all normal structures is 1. So in such a case, we have looked at cyclonic simulations quite extensively, and what we found out is there is no speed increase as per our simulations. And we are suggesting that there is no such increase required, which is very clearly explained in the last webinar, so I'm not going to get into the details. Basically, our suggestion was to live with the K1 factor rather than bringing in another factor K4 into the picture. So this is another suggestion which has been already discussed before. And few other factors coming into picture, which is area averaging factor, which you might be knowing this particular table, which is already in the code. This is something new. Basically, it is applicable only when calculating loads on frames. Basically, you are calculating loads on walls or with some tributary area, you can reduce the loads, which makes sense, which is also in the Australian code, exactly the same ratios. So larger the area, lower the load. Why? Because you have lack of correlation of pressures happening in a very large area. That is the reason we are trying to reduce the load. So basically this can be utilized for when you calculate loads on roofs and loads on walls. It is possible to utilize this particular factor. But we shouldn't be using this factor for calculating lateral loads on tall buildings. And these things are not clear right now in the code, so probably we want to make it clear next time when we do the amendment. That is why I brought this in. Now the combination factor, this is something new came up as well. The combination factor, KC 0.9 is recommended when combining external pressure with internal pressure. When you calculate loads on walls and roofs, you are combining external with internal. What is happening is the external and internal pressures are not happening at the same time. And again, that is lack of correlation. So make perfect sense to use 0.9, but we have kind of limited to only this. We didn't talk too much about whether we can utilize this for lateral loading or not. But Australian code is very clear. They have a big table on KC where the 0.9 can be even applicable even in finding lateral loads. That means there's a 10% reduction is possible. This is something that we should be thinking in the future. I would recommend to utilize this even for finding lateral loads on tall buildings. KD factor is something new we brought in, and we say that, okay, 0.9 can be utilized, which is, I mean, the American code is using 0.85. So we said 10% reduction. And for circular forms and cyclone affected areas, as well as local pressures calculation, we should not be using KD of 0.9. The code is insisting us to use 1. I would say that this is another area we should be thinking. And in my opinion, regardless of this, still there is a reduction possible, in my opinion. That is something that we should be thinking in the future as well. Interference factor is something new, again, brought in. I think I got a number of calls on interference factor, accounting for basically amplifying the load because of another building in front of your building. This is more like, you can say, wake turbulence, more like wake turbulence. But unfortunately, the trouble here is there is lots of parameters influencing this. That means the shape of the building, the distance between the building, the terrain of the building, you name it. There is so many factors influencing. So that is why it is kind of difficult to codify this, in my opinion. And also another problem is, in reality, seldom two tall buildings interference takes place in the field. So how many times that we are going to see only two tall buildings happening? Very, very seldom. So that is another issue. So earlier version of the Australian code had this stuff in their code, which is 1989 I'm talking about. Then they moved it to the handbook for reference, basically. So if you want, you can use it, or you can try to kind of preliminary, do some preliminary estimations and etc. But I strongly say that in some of these numbers, which is also in the code, like Z3 and Z4 zones, it is too high, in my opinion, based on my experience with the wind tunnel testing. So all I can suggest is wind tunnel testing is the only solution to find out the real interference factor. And if you use these factors, which is already in the code, to estimate loads, I'm quite sure this is going to be super high, high loads that you can arrive at. Now I move on to local peak pressures. There is a number of things to cover. You can see at times when the storms are severe or even not very severe, you are losing windows, you are having cracks on windows. Some of these diagrams I'm showing is right from India after storms. So here the issue is that the storm speed did not increase the code speed. So why these windows are failing, which is something that we have to look at it. There are workmanship issues and other issues which I'm not going to be talking about here today. But my interest is more on table 5. Table 5 has a local CPE factor, which is ranging from, you can say, -0.8 to -1.25. We have only one zone, basically, to calculate the peak pressure. We don't have a positive value as well, which is also important as far as framing is concerned, which is not there in the code. We have done some car building model tests. This is a very standard building model test, which has been utilized all over the world. And then what we found out from these tests is that the factors are very high in comparison to the code, especially on edges. We looked at the edges and we are finding values of the order of 1.8, 1.5, even 2.4. Those are kind of isolated hotspots. But then I also compare against the ISSE as well as Australian code. And Australian code is ranging from -1 to -1.95, while the ISSE is going from, I would say, -0.9 to -1.8. So they are all having two regions, one for the middle, one for the edge. Edge is always subjected to high sections. But unfortunately, in Indian code, we have only one value, that is throughout the facade. So what it is showing is basically it is underestimating the load at the edges. That is one of the issues which we talked about earlier as well. We looked at positive values as well. So when you look at positive values, we are okay. I mean, if you use 1.2 positive for the facade, all over the facade, I mean, it is good for design, but we have to put it in the code. And we looked at a number of buildings. I'm just showing a sample 4 buildings. And you can see the wind tunnel range versus IS. Wind tunnel range is from, you can see the first building from -2.25 to -3, majority of the place. Isolated spots, I'm getting -3.75. And IS is giving -2.23. And you can see the rest of them everywhere. Our peak loads are much lower than what is being found from wind tunnel. And you can also compare these values against ISSE 7. You can see those values are in match with the wind tunnel, or match or slightly different, but it is very close. So this is the reason why I'm saying the edges are underestimated. The loads are underestimated at present in the code. So we need to bring out another table or introduce a new zone, etc. So I'm putting an amendment here for you. I'm showing that the positive values we can put from 0.8 to 1.25. The negative we can, for the general zone, we can put it exactly what the code is suggesting right now, minus 0.8 to minus 1.25. But the edge zone, we cannot use minus 0.8 to minus 1.25. We have to go from minus 1.2 to minus 1.8. That means for tall buildings, we'll be using minus 1.8, which is similar to, not similar, I mean, it's identical to ISSE 7. We have all the proof. We are not going exactly equal to the Australian code. Australian code is even higher at minus 1.95. We probably don't have to go there, but we have sufficient proof for this. And what the edge zone means, edge zone is approximately 10% of the least horizontal dimension or 1 meter, whichever is less. So the closest edge is, this is something debatable, which we can discuss later. Probably I don't want to discuss too much at this point. The point here is the edges are already underestimated in the code. Now I move on to long wind loading. So now we are getting into the structural aspects of the presentation. So the long wind loading means basically the wind is pushing the building is oscillating in the direction of the wind. And there are three components: mean, background, and resonant. Basically, these two are the fluctuating components. This is the mean component. The code is built basically according to this equation: gust factor is equal to peak long wind loading divided by mean long wind loading. Very simple. So once you find the mean long wind loading, just multiply with the gust factor, you got the peak long wind loading. It is as simple as that. So there is a great initiative, great formulation, there is no doubt. Look at how we are working closely with other code. For instance, this is the first line is IS 875 versus the second line is the Australian code. So in our code, we are using V bar with G. That means we are using mean hourly speed with a gust factor. And Australians are using peak 3-second speed with the C die. So what I'm trying to say is V bar with the G is equivalent to V peak with the C die. The rest of the parameters are all the same. CD is supposed to be the same, even though there are differences, which is coming very soon that we'll be discussing. But essentially, the formulation is identical. There is no difference whether you use mean hourly speed or 3-second speed. You cannot mix it very easily. If you want to use this particular equation, you take your V bar, convert it to V peak, then you can utilize this equation. You can still get the same answer. Or you want to go backwards, you can also just do the wind speed conversion, then utilize that particular equation. This is the most important, probably out of one of the stuff from this presentation. Force coefficient. This is figure 4 from our code. We went ahead and did even H by B infinity. We have H by B 20, etc. All the graphs. You can see around this region, A by B 0.5, 0.6 region, it is getting super high numbers. And these are very high CF coefficients. And this is not occurring in reality because we have been testing buildings for the last several decades. We have tested buildings up to aspect ratio 23 so far. We never seen anything like this, any coefficient which is happening like this. So we have to immediately look at this because otherwise we'll be overestimating loads, especially long wind loads on tall buildings. So that is why I brought this stuff into picture. You can see what the Australian and ISSE is doing. You can see H by B for all scenarios, and here height limited to 200 meters. With A by B, the plan ratios, you can see the maximum is 1.3. That seemed to be a really good number because based on the testing that what we saw, also 1.3 is ultimate. You cannot get more than 1.3. unless otherwise you are super slender or you are getting into 2D flow with no turbulence in mean uniform flow or something, there is a chance that you can get higher. But otherwise, in boundary layer flow with normal, normal means H by B even up to 23. I mean, I am telling you 23 is ultimate we have tested. You cannot get more than 1.3. So IS 875, look at where we are. I mean, I don't have to, I'm just putting only less than 10. If you go more than 10, what will happen? You can see from your graph itself. It is getting super high numbers. I think this is something we should be attentive and we should be changing this immediately. I'm also putting another graph. This is a bit theoretical here because you know the G. I'm focusing on the G. The gust factor has two components. And I want to focus on the two components. Those two components, one is background, another one is resonant. It's very easy. I mean, we don't have to think about each one of those parameters. Just background and resonant. Background is oncoming turbulence, you can say, and resonant is inertial component, which means the structure is talking with the wind and wind is pushing the structure and back and forth interaction. That is what this resonance means. And look at the gust factor equation between IS and Australian code. The gust factor equation, I'm putting this particular, the left-hand side of the IS 875 is a background. Oncoming flow turbulence and some self-induced turbulence is part of this equation. And the right-hand side is resonance, motion-induced turbulence. And if you look at the Australian code, exactly the same equation. The only thing is they do have 1 + 2 GVIU on the other side. Why do they have that? Because they are using peak 3-second speed for their calculation. We are using mean hourly speed. They are using peak speed. So when they are using peak speed, they should be using that. So essentially, underneath there is an equation saying that G is nothing but C dyne into 1 + 2 GVIH. So it is identical equation. Okay, we don't have to worry about that. Identical equation. The only thing is we are using mean hourly speed and they are using 3-second speed. So we don't have to worry too much about these equations. It is almost identical. Of course, there is some differences, which I can't say why we made it different. Okay, that is another thing probably we should be discussing at the time of amendment. There is an example for you. There are two buildings side by side. This is in Chennai, a fairly rectangle building. You can see what we got out of the wind tunnel. The wind tunnel numbers, there is an underline red there. And then you can see IS 875 numbers. There is an underline red as well. You can see the wind tunnel is slightly lower than IS. And it's that could be due to the surrounding structure, sheltering. But look at the code, the comparison between the codes, it's almost identical. So we are getting relatively similar numbers between the codes, which is great as far as your CD is similar. If your CD has a problem or a CF has a problem because of the figure 4, then obviously this is not going to happen. So the formulation is all okay. So we need to fix the CF. Once you fix the CF, we are going to get identical numbers regardless of which code we are going to use. And I am also putting the G from IS versus the G from AS. You can see again similar numbers. So we don't have any issue with the formulation of along wind, except slightly few differences here and there. Our problem in along wind is purely with CF. So that CF needs to be fixed. Now, the more interesting stuff on Crosswind. This is something new which Dr. Prasad already mentioned in the code. And again, I mean, we borrowed a number of things from Australian code. And so what is meant by crosswind? When the wind is coming and hitting the building, you are getting vortex shedding on both sides of the building. And as a result of that, you are getting a crosswind oscillation. So sometimes in certain buildings, crosswind is dominating. Along wind is much, much lower. I can tell you in certain cases, crosswind can be double or even more than along wind. So we need to be careful about the crosswind. So the code came up with diagrams, for instance, picked from the AS code. And then when we tried to compare, basically, I was being informed that we are continuously getting higher loads from the IS diagrams. That is when I compared and found out that the graphs have been shifted. So you're supposed to get a peak at about 11, but we are getting peak at about below 9. So as a result of that, we are getting too much higher load because our building is lying between ratio 2 to 6 or 2 to 8 in that region. Unfortunately, because the graph is being shifted, we are getting higher cross wind force spectrum coefficient, and that is causing the higher loading. And the interesting thing is, I do not know when we do have the 2011 code version already available, why we went back to 1989 version and picked the graphs. That is something to be discussed, because we could have easily used the 2011 version code equations rather than these graphs, because these graphs are very dangerous. These are in log scale, and depending on the day, depending on who is doing the calculation, you can come up with different numbers. That is why it is better to use equations rather than graph. We looked at a case. This case is from Mumbai. This is a square building, approximately 180 meters tall. And you can see the red line. Again, the crosswind, you can see IS crosswind versus the moments that you can compare from the wind tunnel. It is double, more than double. Then you compare the AS values underneath the red line. You can see it is very, very close to the wind tunnel. Because this is more like a textbook type problem. You have a square structure without balconies and etc. You are supposed to be almost equal to the code. Of course, if some upstream structure is obstructing the flow and etc., you're going to get different numbers, I agree. But otherwise, you should be getting very close. So this is very clear why this is happening, because the same equations from the same graph from 1989 I have used, and I'm getting very close numbers compared to the wind tunnel. And the same graph we are using in IS 875, just because it is being shifted, we are getting a higher number. But I'm not going backward on the 1989. I want to go a little bit forward and to look at, can we use 2011 version of the code instead of 1989 version of the code? We can, and I am proving it right here. I'm using the equation across wind base overturning moment from the IS code versus the AS 1170.2. You can see one-to-one comparison, you can make it. You can see the pH is nothing but in their equation. This whole thing is just pH. And 3 by K plus 2 Km is nothing but 1.06 minus 0.06 K. So essentially, these two equations, 1 and 2, are identical. There is absolutely no difference. So why can't then we use those, instead of using the graphs from 1989, we can utilize the equations. Then everybody is going to get the same answer. Vn, which is the reduced velocity, Vh bar is nothing but V designed by 1 plus GVIH. I will leave it for your thoughts, and these presentations will be available. You can go back and check these equations, and you try to comprehend yourself. And I'm 100% sure that you could utilize those equations. And those equations are beautiful. You can just plug in those numbers of Vn, and then immediately you'll get your CFS, and you can continue with your computation. These things are perfect, but you had to I wanted to remind you that how many buildings are going to be rectangles and squares. So that is a question which I think we need to be really looking into, because every time you have a building with offsets, balconies, insets, and all of those things, then all you're doing is just take Bx and By and you plug in this equation, you get a CFS, you calculate. But the wind is not going to probably be so forceful in those cases. So look at a case where I wanted to also show some cases. These are, some of these buildings are really tall buildings, 500 meters, 364 and 275 meters with some interesting shapes. And essentially in these buildings, if I use BX, BY and calculate it, definitely I'm going to get crosswind. But aerodynamically, there is no crosswind on these buildings. Basically, long wind is governing just because of the shape. So what I wanted to also write in the code, or I suggest for the code writers to write in the code, is depending on the shape, things are going to be different. It's not going to be the same. And another thing is immediate surroundings. Buildings are not coming with single buildings, as you know, with lots of other buildings surrounded. Then again, it will disturb the vortex and it will disturb the flow. And as a result, your crosswind is going to go down. Then dynamic properties have an influence too. So I want to caution you, when you are calculating crosswind, you have to kind of account the shape, account the surroundings, account the properties, and then you you have to make a kind of a judgment call, I would say, which is kind of difficult. But I'm saying that we should not worry too much about those numbers. We wanted to comprehend more than those numbers and what could have been really happening in the field. Now, torsional loading. There is IS 875 silent on torsional loading. And I'm just showing a graph showing an anatomy of mean torsion happening on a square building. I don't want to go through the explanation, but you can see when at a particular angle of attack, sharp separations happening at one corner is trying to twist the building. It's a very self-explanatory. Then you will get a positive torsion. Then when the flow is coming from another angle, the separation is happening at another phase. Then it will alternatively twist in the opposite direction and vice versa. It keeps on going like a sinusoidal wave. And basically in torsional calculation, the eccentricity, the torsional eccentricity is a prime parameter. And you can see when the buildings are going from square to rectangle, it is going to increase the torsional eccentricity further and further. And your loading is going to get increased. And also when you have kind of an L-shaped building or a building surrounded by another building, then it will alter the flow and you can get an eccentricity which is higher. And I'm showing an example just below. There are different buildings I'm showing. And from internal tests, we are getting eccentricity between 9 to 12% in these particular cases. You can calculate torsional loading. I'm giving in a simple equation. You take the maximum shear, Fx or Fy, multiply with the maximum Vx or Vy, which can be averaged throughout the height. Then you multiply with an eccentricity percentage. And that percentage, based on my experience, it varies from 5 to 25% based on number of tests in the last several decades. Typically for square building, eccentricity is small, and as the width getting larger, it will increase. But we can't be playing with these things at the preliminary stage. And so I would propose that you use a 15% eccentricity at the preliminary code calculation stage, which is also suggested by ISSE. Now the last bit, load combinations and some of the miscellaneous items that I want to be presenting. Load combinations, and I'm showing ISSE 7 and Australian code as well as Indian code. Some of these ISSE 7 diagrams, case 1, case 2, case 3, case 4, in some cases, they are applying load only in one direction, 100%. In this case, they are using, in the case 3, they are using 2 sways, but at 75% each. Then in case 2, they are using 1 sway and with a torsion. I'm giving some percentages. And then in case 4, they are using 2 sways simultaneously with 56% and 100% torsion in that case. This is very similar to what you'll get out of the tunnel too. But all I wanted to remind you that wind is not going to be acting like case 1, case 2, or case 3 cases. When wind is blowing against your building, definitely it is going to cause X loading, Y loading, and torsion loading simultaneously. The only question there is on what proportion. That is the thing that we need to answer. What is the proportion that it is acting? That we will talk in a bit. Australian code is saying, okay, you separate the mean, then you combine the fluctuations, the crosswind fluctuation and the long wind fluctuation, you take a square root of that, and then add to the mean. Without torsion, they are suggesting the load combination. Indian code went one step ahead and too conservative, I would say, because we are doing 100% along wind, 100% crosswind. This is not going to happen at all. So this is not real, okay, because these loads cannot occur at the same time. Lack of correlation between forces happening at two different directions. The things are not going to happen at the same time. So we have to be very careful on that. Some of these points which I just talked is written here. Lack of correlation between forces at different directions. This is the point that we want to raise. We have been testing buildings for the last several decades. We have found ratios going from all the way from 30% to 70% in some cases. But I would recommend that we use primary component 100% with 50% from other directions as secondary components. As a first cut scenario, when you do the wind tunnel test, probably it can range anywhere from the secondary components from 30 to 60% or so. A few more things. I wanted to stick with the time, not to exceed the time too much. So structural damping, there's a lot of confusion in this. Depending on the code you look at it, and depending on serviceability or strength and ultimate, etc., etc. ISSE 7 now, as you know, 700 year to 3000 year return period, 300 year to 3000 year. So they suggest that ultimate damping, we can use 2.5% to 3%. AS, Australian code is very clear. RCC is 3% and steel is 2%. And then with IS 875 and you can see RCC 2%. And steel, they separated into bolted steel and welded steel. And they also suggest pre-stressed concrete to 1.6%. And in RWDI, we have been utilizing this RCC 2%. For this case, it is 50-year or 100-year return period, composite to 1.5% and steel 1%. And in serviceability also, there is a confusion. Various numbers I'm proposing, I'm putting it here, like ISSE 7 and Australian standard as well as international, and IS is kind of silent on that, and RWD uses basically RCC 1.5%, and steel and composite we always use 1% as damping. Return period is another confusion that comes in. What is return period? I believe that itself is a confusion for many people. When we say 50-year return period, some of us will think that, oh, this storm is going to appear only once in 50 years. That is not correct. What that means is 50-year storm means the chance of occurrence of 50-year storm in any given year is 1 by 50. That means the chance of occurrence of that storm in this particular year is 2%. That means this storm can happen or cannot happen. There is a 2% chance that it can happen or it can exceed, right? And it can happen number of times too this year. It can happen number of times. Probabilistic, this is a probabilistic term. So we have to think in a probabilistic way. So strength design, ultimate return period, ISSE 7 is using 700,700. Australian is using 1,000. You can see for strength design, but their factor safety is 1. Then with American code and the rest of the codes, like including us, we use 50-year return period. Then we use a load factor of 1.5 or 1.6, depending on the code, even on 0.4. So this is very traditionally, this is happening. But lately, there are a number of confusion on the serviceability side. ISSE 716 now suggests anywhere from 10 to 100-year return period. That is more like performance-based design. So depending on your appetite, basically you can use 10-year or 25-year, etc. But previously 705 was using 20-year return period. Australian standard is using 25-year return period for a long time, and NBC same, and IS lately I think we put 20-year return period in 16700. But when it comes to acceleration, there is not much confusion. We are mostly standardized 1 and 10-year return period, even though in our code, I think there's a 5-year return period return that needs to be amended in the future. Acceleration, we are putting it here, the equations. Essentially, we are grabbing from other codes, NBCC 2015 for a long wind direction. You can, I am not going through all the details. You are going to see this particular presentation again later. You can access it and you can digest. And 5-year return period and 1.1% damping is something that we need to address because we want to put 1 and 10-year return period, and also the damping needs to be changed to 1% to 1.5% depending on the structural material. Crosswind is directly picked out of the code from Australian, and we can use equations, not the graph. Okay, I'm underlining no graphs and only equations that can solve all our problems. The current problems, the problems are all not going to go away depending on your structural shapes and things like that, which I think all the codes are on the same page on that particular matter, because we are no different than the rest of the codes. I'm almost at the closure now. Concluding remarks. Basically, wind profiles need to be updated. I told you the profiles seem to have differences between the codes. So we need to address that at some point, because sometimes we could get mostly higher reference pressure, it looks like. And I do not know the reason behind that, but we need to address that at some point. And then local wind pressure coefficients must be changed. I told you the edges are underestimated. We have values much lower. We need to be extremely careful. Otherwise, the windows at the corners can be underestimated in design. And appropriate force coefficient is another issue. We are overestimating that because, as you know, A by B, somewhere around 0.5, 0.6 region, it is quite high. So we need to address that. And there is lots of information out there. It is very easy for us to address that. But we have to do it ASAP, because otherwise we keep using those numbers from the code. I would say interference factor section shall be removed, because I don't see much benefit for those sections. And we can put it in some guidelines or as a guideline or a handbook if we have one, but not in the main code, because this is getting kind of confused. And if you want to put it, I would say at least you put some reasonable numbers, because I personally feel Z3, Z4 sections are super high numbers. Equations corresponding to a crosswind force spectrum coefficient shall be adopted. It is very clear, already been proved that it can be used. And you also try it out. I mean, you don't have to listen to me, what I am saying. You can do it yourself and get confirmed that it can be utilized or not, and go through this presentation again with the equations present and digest those equations. Torsion loading must be introduced, and we don't have to wait for other codes to introduce. We can introduce ourselves, and this is all known. I mean, some codes are already introduced, so we don't have to wait for all of them to address this stuff. This is a true loading, and we need to address this loading. The last one is load combinations. It shall be introduced very clearly so that there is no confusion, and we can all enjoy appropriately combining the long wind, crosswind, and the torsion loading together. And I hope you enjoyed, and I don't want to fill it with stuff. And you can ask questions, but finally, if your question by chance, if it is not being addressed or something, you can always contact me. The email address is written here, and my number is also written there. You can call me as well. I'm more than happy to answer. I think I got some questions already yesterday from some of the viewers today. So I have been answering those questions already. And knowledge is for sharing. And that is what we are trying to do here. And no offense to anybody. Some of these numbers are real numbers. You can go back and check it. And we wanted to better our code for the users and try to do a good job there as well, so that we can say our codes are robust and things like that. Thank you very much.
Thank you, Suresh, for your insightful presentation and coming up with specific suggestions. And it is important for us today to note that Dr. Suresh's talk is based on numbers obtained from the practical case studies with the different plan aspect ratios. He also compared the numbers with the different codes and wind tunnels. So here, actually the numbers are speaking for themselves. As structural engineers, as structural designers, we are ultimately interested in the total base shears in both directions and in the base shears movement and the torsion. So today we have an interesting presentation here where Dr. Suresh has come up with basically a practical case studies and very comprehensive compared with different codes. And also there is a wind tunnel test data for verification as a backup. So this presentation comprehensively covered every parameter that influences the design loads for tall buildings and wind profiles in different terrain categories, the directional winds, interference factors, along wind, across wind, and torsional effects. And he also touched upon the load combinations and he commented on the local pressures for cladding design. When I see the entire presentation, with an exception to the local pressures, there is an element of conservativeness or a point to look at in Dr. Suresh observations and study results. So when it comes to the design of wind sensitive structures, we always need to keep in mind that it is a very complex fluid structure interaction, which is a dynamic interaction. Methods have vastly improved during the last few decades, from simple static wind load to quasi-static approaches, and then to the refined dynamic wind load for more wind sensitive structures. The purpose of the code, I mean, for that matter, any country, the codes of any country is to provide, as far as practicable, simple analytical procedures for the determination of wind loads for a broad class of structures, as wind load designs cannot exhaustively cover all the shapes and sizes and in every case. Building codes and standards as such, they do continuously evolve to reflect the state of the art research and also to meet the requirements of practice. See, for example, we don't have buildings, tall buildings in our country a couple of decades back. But now when we see in places like Mumbai, there are tall buildings everywhere. So for example, 1987 revision brought in the gush factor approach, and 2015 revision had also paid attention to serviceability related requirements such as restrictions on accelerations. This is apart from the across wind. The tall building code 16700 provided restrictions on displacements and interstory drifts. And from today's presentation, we understood that some more changes are needed in our 875 code, specifically on the assessment of the wind climate and the way we account for the modifications for local topography, terrain category, and the structure size. The area averaging factor, Dr. Suresh suggests not to be used in calculating lateral loads on tall buildings, which is a very important observation. Similarly, he has clearly put forward his use on the newly introduced that K4 factor for cyclonic areas. And concerning these cladding loads, the code is underestimating the pressure values on edges. So two specific suggestions from Dr. Suresh are, one is zoning. The other is the increase the coefficients by 50%. Until this is done, we as design engineers, we need to be cautious when we are arriving at the forces for cladding from the 875 provisions. And in the along wind direction, the analytical procedures incorporated in the code is quite rational, but the problem is with this CF, it appears to be very high for certain configurations, and these configurations actually lies within our practical range. So, for example, the building square in plan, wind forces, the along wind could be very conservative. And estimation procedure for across wind response need revision. So there is a discrepancy in figure 10 plot. Also, it was suggested to simplify calculations. See, this is for the design practice based on 2011 Australian code rather than following their 1989 version of the code. And he also suggested the need for considering the torsional effects and in the form of load combinations. And he also he has given his comments on the simultaneous application of sway forces and torsional loads with the combination factors shall be included. In summary, it is vital that the review and update of the existing provisions of 2015 code related to wind sensitive tall buildings shall be carried out at the earliest. For some reason, say to account for uncertainties, we always do, even in our design, we keep a factor of safety as engineers. If we want to be conservative, it is better to limit this conservative approach to say one key parameter, rather than being conservative with respect to multiple parameters. I do hope that the suggestions will be considered and incorporated soon into our code. Now, I request Dr. Mahua Chakravarti to give her observations. Later, we will take the question and answer session.
Thank you very much, Dr. Prasad, for a very exhaustive coverage of the whole talk by Dr. Suresh Kumar. I would like to first of all congratulate Dr. Suresh Kumar for such a lucid explanation and such a logical explanation of all the points taken in the proper order, and he has exactly brought out each and every aspect very, very clearly for all of us structural engineers. I would also like to thank ISSE for arranging such a relevant and interesting talk on an important topic like this. Now coming to my role as I have to give some remarks on the relevance or the relation of this lecture with reference to the high-rise buildings. As we know that high-rise buildings are sensitive to wind loadings, and as already explained, there are many features about the shapes, the wind velocities, and the planning and the facades and all that, which has already been covered, the load combination, serviceability, strength, and so on and so forth. Now, as part of the reviewer or the administrator who is going to look at these high-rise designs, our role is to stick to the existing codes of practice. So we have to abide by all the rules and regulations of the code, even though we know that there are, there is scope for some modification or some rectification. So as long as the code exists, we have to see that the code is followed. Now, as a structural engineer, my take-home point from this presentation would be that the torsional effect of the wind loading should be as small as possible, and for that we have to work in unison with our architect friends and see that there is very very less amount of eccentricity as far as possible. If we can reduce this eccentricity between our center of mass and center of stiffness, I think that will help us in a very, very big way, especially in this situation where, torsion has not been taken into account in the latest revision of IS 875. I think with that, I would like to end my remarks. Thank you once again, ISSE, Dr. Suresh Kumar and Dr. Prasad. And I think now it's time to go into the questions. Thank you.
Thank you. Thank you.
Thank you, Dr. Chakravarti, for your good observations. And now we'll have our question and answer session. And we are getting several questions. The list is ever increasing, and we'll take up some important questions that are relevant to the current topic of discussion, that is wind on tall buildings. First, let me start asking my first question on the terrain category. That's Suresh, you mentioned that category 1, category 4, and especially say, for example, the place where right now I am sitting very close to the seashore. And in our locality, say for one building, is it possible that we use different categories, with different terrain categories over height for the same building?
Definitely, I think that is one of the cases which we have it in our code, which is very interesting because I didn't brought that up. That is one table 3. Table 3 has fetch and developed height relationship. So in a couple of cases in Mumbai, what I'm seeing is that the building is about 2 kilometers away from the seaside. I have a number of cases that we have done in Mumbai. What is happening in those cases is the wind is coming from the ocean, and then because of the terrain change, it gets changed to a certain extent when it hits the building. So what we observe is, let us say the building is 300 meters tall. Maybe the bottom 150 meters is the terrain category 3, and the top is terrain category 2 or even 1. So we can always get a mix of terrain categories depending on where our building is, where the building is located, and depending on the height of the building as well. Let us say on the same spot, I have only a 100-meter tall building, or let us say 70-meter tall building. Maybe the entire building is engulfed in the terrain category 3. We don't have to even consider 1 or 2. So that particular table, I would advise everybody to look at it. That is something really useful to judge what is the appropriate terrain category for your location. It's something to be utilized.
Do you think there need to be an explicit mention of this in the code, that different terrain categories can be used in one building?
We can address that. Actually, see, sometimes when we give the table 3, but then we don't give any instruction, I don't know how many users are really using table 3. They'll be bypassing table 3, because if there is a table without mentioning the use of the table, then obviously you don't use the table. So that is where the trouble is. I mean, we have to look at each table and see where and when we can apply those table values, when the values inside the table. So we have to explicitly give a couple of sentences saying how to utilize that table. So in that way, we can sort out this issue.
Okay, okay, thank you. The one next question is on the crosswind.
Yeah.
Like, you compared the crosswind, the numbers with the Australian code, but not with the American code. Apparently, ISSE does not have these provisions, or it doesn't want to depend on the analytical procedures for crosswind. Any comments on the rigorousness of these analytical procedures?
The analytical procedures inside the AC7?
They are not, there are no provisions for a crosswind in the AC7.
Yes. See, why I am comparing again, with the Australian code is basically we are directly absorbing from the Australian code. There is not many code addressing a crosswind at all, actually. Number of codes are not addressing a crosswind. The trouble why they are not really addressing that is things can change very easily, because let us talk about a long wind versus a crosswind. In a long wind, even if you have buildings in front of it, even if your terrain is very complicated terrain, you can do a reasonable prediction with a code, okay? Because things are not that complicated. The complication comes in terms of, let us say one of the building is very closer to your building, that will give some shielding. So because of the shielding, your drag coefficient will be slightly lower. But because the building is too close, it will increase the turbulence. So you are reducing your mean and you are increasing your turbulence. And after doing everything, you may come across similar loads. Things are going to be similar. So in long wind, it is quite easy to kind of predict, unless otherwise some peculiar scenarios, But in crosswind, that is not the case. In crosswind, not only is the shape, the surroundings, the shape is very, very important. The surroundings are important. Your properties are important. So many things are important, and then you can completely miss it, okay? And you can completely overestimate it too. So that's the reason we have to we have to be cautioned. For instance, I'm trying to combine now the long wind and crosswind. Let us say we have some suspicion on the crosswind because of the way the shape is, because of the way the building, where the building is located. There is an easy solution. That easy solution is when you go through the combination, you have, instead of having a long wind and a crosswind combination, you have FX, FI, and MZ. You say that, okay, I wanted to maximize my FX and I want to take some FI. That FI could be 50% of your long wind FI, right? 50% of your long wind FI because you have some doubts on your crosswind FI. That is the reason you go for, because you wanted to consider some loading in that direction. So you are not going to completely miss that loading, because if you have too many surroundings and which is blocking, and you have a shape which looks reasonable with some balconies and disturbing the vortex, and you are not going to get a high crosswind, why not we use 50% of the long wind load, So there are ways to take care of that, but we need to go into that.
Yeah. And the ISSE clearly states that buildings expecting the high dynamic effects from vortex shedding, we need to go for wind tunnel studies,
Yes.
That's their recommendation is.
Yes.
See, the next question is on the fundamental modes, the building modes.
Okay.
See, engineers prefer to keep first 3 modes of vibration to be distinct and uncoupled. but this is always not possible.
Yes.
And so coupled modes, you said sway winds and torsional forces simultaneously act,
Yeah.
But their peaks does not happen at the same time.
Yes.
So in what way distinct and uncoupled modes will help here?
See, coupled modes typically can increase loads. Okay, the rule of thumb is the coupled modes typically increase the loads because when, let us say, FX is happening in one direction, it is kind of feeding into FI, it is kind of feeding into torsion. So it is getting a component. from the X itself, when the Y is happening or the X is happening, for instance, the X is happening, wind is hitting in the X direction. If it would have been an uncoupled mode, we are supposed to get only the X, resonant wise. Be careful what we are dealing with. We are talking about only resonance. When we are talking about modes, we are not talking about background. We are not talking about mean loading. We are talking about only resonance. So we are talking about resonance, which is supposed to be happening only in the X direction. But when it is coupling, it will feedback. There is a feedback to the Y direction as well as torsion if it is all coupled. So that feedback can give a higher loading in the Y direction as well as in torsional case. So uncoupling would really help. But we need not worry too much on those things. We are not getting into the wind tunnel. In wind tunnel, of course, we look at all the coupling and etc. But when we are in the codal application, we cannot account for the coupling. It is difficult to account for the coupling. Probably that is another reason that we wanted to make sure that we take 50% of the FI. Even if you don't have the FI, you go for the 50% of the FI along wind, and then you also take 50% of your torsion. And by doing that way, you're not going to completely miss out of all the stuff. Okay, because so many unknowns, like this is one of the unknown actually, how these things are interacting, and we don't have any idea to, we don't want to do testing for all buildings, and we don't suggest it as well, but we have to somehow cover it here and there, because otherwise, basically we are asking for trouble. And sometimes we have another thinking which is out there in the community is that my building is only 110 meters, I don't have any issue. And that is wrong, actually. That perception is wrong. I have seen number of cases where 110 meters is having trouble because of another building sitting beside it. So in those cases, if you don't do wind tunnel test, how do you cover it? This is the only way that you can at least cover some of those issues by taking care of your FI and by taking care of your secondary components. Basically, you take care of your secondary component. Then you are not going to completely miss out things.
Okay. So this is another reason, why we are expecting a change in the load combinations.
Yes, exactly.
Yeah. The next question also is related to the modes only.
Yes, go ahead.
See, we normally we try to keep the rotation as a third mode.
Yes.
Again, this is not always possible.
Yes.
You see, sometimes what happens is one of the translational modes, say in the longitudinal direction, I have way stiffness in the building. The building is very stiff.
Yeah.
Because of that, the third mode, comes and occupies the second position.
Okay.
And so the point is, it's not always possible for every building to ensure that to shift the rotation to the third mode.
Yes.
And basically, you have covered the accelerations, but what the effect of this third mode, rotational mode, on torsional velocities?
Right, understand. See, there is also a confusion out there on torsional mode. From earthquake point of view and from structural point of view, I don't commend it. From wind point of view, even if you have the torsion being the first mode, even though it is not the preferred way of doing it, but it doesn't really matter. Doesn't really matter as far as wind is concerned. If your mode is coming, torsion mode is coming first. We have done a number of cases like that in the past. Because, especially in certain cities abroad, not here, torsion mode is always the first mode. You know the reason? Because the periphery, there is nothing there on the periphery. You don't have any structural element. Everybody wanted to have large windows at the corners and etc. No structural element. There is no torsion stiffness. Only you have the core, and the torsion stiffness is not there. But they are all facing the issue is torsion velocity, because they are all facing torsion velocity. In number of cases, they had to go for a damper because they don't want to. They don't want to change the design because they want to have high-end condos selling, etc. So they all have torsion velocity issues. even though the speeds are low. Actually, in those cities, I know certain cities, the speeds are low, but torsion velocity issue is there just because your first mode is torsion. And they said that, okay, we don't have any choice. We have to go for a damper. So we designed a damper to take care of that. Basically, because there is no torsional loading issue, okay? We have to be careful. We have to separate these two things out. So torsional strength design-wise, there is no issue. There is a high torsional affecting, but they will take care of that design. Their issue is mostly on the motion, and that motion can be arrested using damper, and taking care of torsion through damper is also not very easy, because translation is very easy to take care through dampers. Torsion is slightly tricky, but we can do that. We have done it in the past, and that's the only way, unless otherwise you change your structure.
Yeah, and the tall buildings, in most of the cases, the design is governed by the wind load rather than the seismic loads.
Yes.
So that then, I mean, as per this discussion, there is no need to worry about this torsion in which position it is, right?
Yeah. Right.
Okay. So now I there are certain questions from the participants.
Yes.
And one question says, what happens to the wind load of my building when a new tower comes after the construction of mine?
That's a good question. I think you see the topography and the surrounding keeps changing. Okay, it keeps changing. And a few things that we need to remember. The rule of thumb, again, the rule of thumb is the lesser the surroundings, the higher the loading. That is the rule of thumb. Typically, when you have another building coming nearby at a specific distance, for instance, I'm keep seeing some comments on the wake turbulence and the interference factor. And that particular issue is happening only for a skewed angles of attack. And over the period of time, the city is going to grow, and you're now going to find any issues. So what I'm trying to say is that the lesser the surrounding, the higher the loading. That is a general rule of thumb. At peculiar angles of attack, you can have some higher loading because you are bringing up a new building all of a sudden. And over the period of time, the city is going to grow, and that issue will go away. In the meantime, you already have a factor of safety already built into your design, and that should be taking care of that. It is not going to go beyond that. All right.
Okay. The next question is on the directionality factor. See, when we use the directionality factor, 0.9 in our calculation, obviously, we are considering the fact that the wind is striking the building at an angle.
Yes.
And it's logical that we need to consider some component of the force in the other direction.
Mm-hmm.
So if we are using this 100% in X direction, and if we don't take any component, then we should not be using the directionality factor. That's your clarification is asked for.
That means if we are not using the secondary components, then we should not use the factors, the directionality factor?
Yes. Is that, is that logical? Is that thinking logical?
In my opinion, that case is not there in my mind at all, actually. I'm sorry. It's not there even in my mind, because the wind is not going to act that way. I think we all have to understand how the wind is happening. Even if, let us say, a square structure, wind is coming, hitting exactly in perpendicular to the face, the flow is symmetrical, right? There is the kind of thinking that we all have. The flow is symmetrical. How can I have a flow in the crosswind direction? Definitely, you have a point. Your mean is zero. I agree with you. Your mean is zero, but you have a fluctuation. And that fluctuation can be super high, okay? And that fluctuation can be super high. And that is your crosswind. That is why we are saying always, regardless of the wind direction, you always have X, Y, Z. There is no doubt. The only question we are asking is what are those percentages? That we keep on debate for a day. There's no issue with that. Okay, but nobody can say that only X is happening, only Y is happening, only Z is that. That's not going to happen.
Okay. The next question is on the damping ratio to be considered for the testing. And for concrete structures, the wind tunnels consider the 2% damping.
Yes.
And for steel buildings, it is 1%.
Yeah.
But what we have today, we have hybrid buildings. We don't build only steel structure,
Yes.
and which is like light in weight. There is substantial mass in the hybrid building.
Yes.
So, what damping ratio you would recommend?
For hybrid, I would say it is more closer to RCC than concrete. We can take the RCC numbers in terms of for strength, we can use 2%. And then for acceleration and deflection, we can use 1.5%. So
Okay.
this is something different than the composite structure, I would say.
Yeah. So any special considerations like, for steel buildings when the engineer arrives at the wind loads from the code?
Special consideration for damping, we always use 1%, whether it is acceleration or strength. And because typically in steel buildings, your damping is less. And in fact, there are lots of measurements happening in the world as well, not too many measurements, but at least there are a number of measurements happen. And especially in steel buildings, we have been finding damping lower, especially as the height increases. And of course, there is a division of welded versus bolted and all of those things, but we don't go with that type of separation, because if it is a steel structure, we straight away use 1%. We can't see getting anything above 1%, unless otherwise you are getting in the ultimate limit state or so, which is 1,000-year return period or something, then probably you can use slightly higher numbers.
Yeah, this is true when the building is tested in the wind tunnel. Suppose
that is true.
Not tested, and if it is designed with the code-based wind. So the distinction that the engineer need to make, what additional considerations you should keep in mind?
I think I would straight away go for 1%. I don't think I'll go anything beyond 1% if you are not doing anything else. So,
but where the basically codes, the loads are don't take into consideration the damping when one is coming up with the structure wind loads, right?
The codes do take. I mean, you have the G, right? The gust factor. Yeah. The gust factor has one of your parameters damping. So the resonant component has that factor. I have it in one of the sheets.
Yes.
So for instance, let me go back to that. This beta, so the beta changes. So whether you are using 0.02 or 0.01, 0.2 is for RCC and 0.01 for steel. So that's very clear. There you can utilize.
Yeah. What is the best method to account for the wind directionality of the sector?
Now, none of the code is accounting any of these things, because the code uses a kind of a blanket factor for accounting directionality. And as per C2BUH, C2BUH guidelines are out there for wind tunnel studies. If you look at there are three methods which is distinctly put in that particular document. One is sector approach, second one is upcrossing approach, and third one is storm passage method, which is, you can also call it direct method. And you can read out there, sector method needs lots of expert hand in order to utilize that appropriately. And there are issues in terms of independency between the sectors and things like that. I'm not getting into the details, but upcrossing is much robust in terms of theoretical based. And we have been using this for the last 4 decades or so. because since our beginning, we have been utilizing this. And whatever tall buildings we have done around the world, I mean, you can say number of skyscrapers we have done. In my own virtual background, 20 skyscrapers I am showing, and we have done 18 of them. All the 18 of the 20 that I am showing right here is applied with upcrossing. It is a robust enough method, and we have been comparing this against the direct method, which is the storm passage method. And we didn't find anything wrong in using this, because the upcrossing is more like an analytical way of analytical approach in comparison to the storm passage, where you are using the actual data itself. So that is my answer to that. I believe that there are other methods people are drumming around, which is out there, but I would say that we should not be too much carried away by all of these things. We have to, I think, being peer reviewed and published and being utilized, and that is the proof basically for which method is the robust method. All right.
Yeah. The next question is basically, what are the chances of installing the wind speed measurement equipment?
This is a very interesting question. I think, see, the wind speed equipment, let us say in Mumbai, we have done some buildings, we have been doing number of buildings. Let us say we put an anemometer at some height in one of those buildings. Unless otherwise you put an anemometer in a free flow. Free flow means your mast should be really tall. If you don't do that, you put just an anemometer somewhere at a 1 meter height or 2 meter height or whatever, your surrounding is going to disturb that flow, and you are not going to get a better measurement. If, let us say, your building is right at the coastal line and you're putting an anemometer even at 2 meter height, probably it is good, or a 3 meter height, it is good. But not in the middle of the city. The middle of the city, if you want to put it, you have to be at least, I don't know, depending on the height of those structures, you have to judge what should be the mast height in order to get a free flow. Because if you don't put the mast at a free flow, I mean, the anemometer at the free flow, your readings are going to be disturbed by other buildings, and that reading has no value. Okay. So it is a good idea. And many times what happens is, if you are putting a damper, likely you will also measure the speed, because you may be assessing the damper performance. And if you wanted to assess the damper performance, you may as well do the measurements as well, so that you can correlate, at what time this acceleration happened, and et cetera, and et cetera. So we have been doing this on a number of buildings abroad. In number of structures, we do have measurements, both wind as well as accelerations on dampers.
Okay. Can we use the CFD techniques for preliminary estimation of the crosswind?
My answer to that is no. Okay, because see, the CFD is a good technique. It can give you probably some insights in how the flow separates, not the separation, how the flow occurs. Beautiful diagrams, you can see it in colors, etc., and etc. But whether those values can be believed or not is a question mark. Just I want to tell you a few facts on CFD. I'm not anything against CFD. We have our own team working on CFD, especially on bridges. We apply CFD a lot in bridges, because bridges are more streamlined bodies, and you can get much better separations. And bridges are not with another building beside it, and etc. So you don't have any disturbances from the upstream structures. It is quite a nice scenario, like you can say wings of an aircraft kind of a thing, So we have been using, and even there, we do have problems. Okay, even in those flat type of structure, we do have problems in getting what we are looking for. We are still struggling. And also when the motion is happening, you have double issues, because in bridges, it is moving. The bridge is going to move and the flow is then hitting the structure, and you need dynamic models and etc. And we know that how much time the computer is going to take in resolving even one direction. okay, let alone one direction. It will take a number of hours to resolve it. And I don't see any quick resolving such a matter through CFD right now. The only thing is we can utilize this probably just to check the flow for internal flows, for outside flows, etc. It is a nice tool to look at it. But if you want to go with the design, I think you have to go back to the wind tunnel, I would say.
Okay. The another question again on the wind tunnel, like, the questions are coming on the wind tunnel procedures. See, how do you, basically validate or benchmark the wind tunnel studies?
Oh, that is much easier because car building model I showed, that is kind of a benchmark study. Car building model has been tested all over the world in many wind tunnels and etc. And those data is already out there. And that is how we found out that the pressure coefficient in our code is having some trouble. It's very easy. We tested in our own tunnel. We compared against other tunnels, etc., etc. And if, let us say, one of the cases where this is not being tested anywhere, which is getting tested here, we do have ways of assessing whether the wind tunnel is doing a good job or not. We can always compare mean flow. We can compare pressures happening at the middle of the phase. See, wind tunnel is only a tool. It's only a tool. Depending on who is using it, depending on the expert mind behind those who are using it, that will have a much bigger importance on the results which are going to come out. It is not a simple tool. Nowadays, wind tunnel is a tool which you can purchase. I can purchase a wind tunnel, very easy. There are people who are selling wind tunnel. I can purchase it. That is a very easy thing to do. But what do you do after purchasing the wind tunnel is a question mark. Because you will always get an answer too when you do a test. But how good those answers are, something that relies on the expert hands which is behind those wind tunnels, right? So that is the most important thing, because many times before the test, I would say that we probably already know the answer. We may be debating, we may be saying this is not going to have a problem. And then after the test, we find a problem. That is when the investigation starts. Because we already expecting no problem with the test. But after the test, suddenly there is a problem. Then we have to go back to the tunnel, find out what exactly is happening, why the problem is created at a particular angle of attack. That is when the real project's really starting. Up to then, the project is very simple for us, So I wanted to tell you, all of you, is exactly like how you use computers. Whatever going in, whatever comes out, and depending on what is going in, how robust your model is, whether you can believe what is going to come out of it. You also have a ways of checking the computer output. Exactly the same way we do have our own checks. Further on, just one more point. These wind tunnel tests have been compared against full-scale measurements number of times. Even the Type A 101 measurements, which is going on for years on the damper, the predictions which have been done about 15, 20 years back still holds true in the Type A 101, which is a great example for what the wind tunnel is doing, because the 15 milli-G per milli-G acceleration, which is being predicted long ago, is still not broken after many cyclones and typhoons passing by.
Okay. See, when you are testing the building located in a cyclonic region,
Yes.
do you take any special considerations while testing?
Okay, this is an interesting question. Actually, the profiles which are in the code is typically for synoptic winds. Synoptic winds with profiles of 0.14 or whatever the alpha that you can calculate, which are typical synoptic pressure system wind profiles. And the cyclonic profiles are a bit more flatter. There are flatter profiles, which you can say alpha when the open terrain is 0.14, the alpha for cyclonic profile could be 0.11. There are lots of values out there. You can check the references. So it is a bit flatter profile, and you can correct it. You don't have to really simulate that inside the tunnel. You can correct that profile analytically You don't have to simulate it because there is a gust correction which can be done at 2/3 height to the building and etc. So that is what we have been practicing. Okay, the turbulence, you don't have to worry too much about it. And this is part of the explanation I have done in the last webinar about cyclonic turbulence, because there is lots of confusion there as well. Our gust factor is very high in cyclone versus in synoptic winds. That is not true. There's lots of measurements out there. Whenever your mean is very high, you get approximately the same as what a synoptic wind gives. So you can simulate exactly the same way what you used to do. But if you are doing thunderstorms inside the tunnel, that is when you have a problem. The profile is not similar. It is very different. You have to do a lot of gimmicks inside the tunnel to create a thunderstorm. Even then, you cannot simulate the turbulence properly. The scales are very complicated. And even now, the research is going on the turbulence scaling for thunderstorms.
Okay, okay. See, Dr. Suresh, as we discussed, this is a very complex subject. There is a fluid structure interaction, which is dynamic.
Yes.
And like, the accelerations, the dampers, and this subject is pretty interesting, even academically also.
Yeah.
And what are your thoughts, like, on the direction of research in this area that, like, this should be going forward?
Oh, that's a great question, Prasad. That's a great question. See, the trouble we are having in India is that we don't have specific courses in wind. I know that IIT Roorkee had a number of things. I mean, number of students came out. I believe that probably there are some courses happening there in IIT Roorkee. I think there are some of the attendees definitely from there. But in the rest of the regions, we don't have courses. For instance, in IIT Mumbai, I'm quite sure there is no specific course in wind. And in fact, I suggested this some time back to IIT Mumbai, but I didn't get any response actually, because everything is happening under the nose of people in IIT Mumbai, but there is no single course addressing this. I know lateral course is there, which probably is addressing earthquake and wind together. But we could have easily come up with a course exclusively for wind and the problems related to wind. This is kind of very urgent, I would say, and also faculty should take these subjects as very serious and do research and bring in students and et cetera, with some good courses in wind, advanced courses and some basic courses. And even in undergraduate level, some electives can be code-based wind course, so that at least they'll know in and out of the code before they come out of the 4 years, because not everybody is going to do masters. And then when they walk into the firms, they know already how to use the code very well and how the code works and things like that. That is my proposal. Okay.
That's very interesting. Like, see, to make the students more interested, like, so now, there are different uncertainties. Now we talked about various, the basis for the calculation arriving at the wind loads are different in different codes. So the student community will have a confusion, like, they cannot look at the Australian code and when the undergraduate level at least. Yeah. And American codes and all that. They look at is our code.
Yes.
So I mean, right from in my opinion, because wind is nothing but related to the fluid mechanics.
Yes.
So the fundamental research need to start from that kind of fundamental thinking need to start from that level itself. While teaching the fluid mechanics, how the provisions, how the mass work for the wind.
Excellent. That is very good. See, that is part of the trouble is with our own curriculum, because when I was doing my fluid mechanics in third semester, we all studied a geometric similarity, dynamic similarity, and Buckingham pi theorem, and Pitot tube, and et cetera. We just studied, and myself at least, I just studied and I got a nice mark in fluid mechanics. I went away, and then later on I realized, oh my God, every day I have to use Buckingham pi theorem. Every day I have to use Froude number. Every day I have to use Reynolds number. That is when I realized that this has a practical application. A pitot tube itself is an instrument which we almost use daily. So the curriculum has to induce these things. When they were talking about these things, at least say one word, this is getting utilized in the wind tunnel, and this is getting utilized on a daily basis when you are calculating, wind loads on buildings and etc. Then, of course, students will get interested, and we can put everything in place properly. Very good point.
See, one last question, because I want to conclude this within. I know you are very particular about maintaining the timings. See, though overall procedure is similar, wind codes of different countries have different basic parameters, coefficients, or subtle changes in approaches. Today, an engineer, basically the Indian engineers are truly working in the international scenario.
Yes.
They are familiar with the countries, the other country codes, and the Australian, American, because they work on various projects.
Yes.
So do you think it is possible to come up with an international model code for wind loads? And if you see, basically there is a possibility, then can bodies like CTBUH, ISO can take a lead in this direction to connect wind specialists like you across the globe and come up with a model wind load standard?
That's a very good point, excellent point. I mean, there have been a number of papers from experts showing how different the codes are, actually. How different, because I can show you a number of papers, ASE versus IS versus Australian versus European versus number of different codes, But, everybody has their own committee and they come up with a code, they write the codes, etc., etc. But you have a very valid point. All I can say is that CTBUH and ISO and international bodies should team up and unify these codes. Otherwise, I would say to a certain extent, the users will get confused. Probably the wind engineers are not going to get confused because we know in and out of each code. We know which code is better than the other code. When I am calculating something, probably we know everything in our fingertips. We accordingly utilize stuff. But the users won't be knowing that. They'll be really surprising why I'm getting double the load compared to another code. For which I think international bodies have to unify on that particular matter and answer that. That's a great suggestion. And I believe those who are listening, CTBH, probably some people will be listening and they should really look into that. Thank you, Prasad.
Okay, now we have come to the conclusion, basically, thank you, Suresh, for your insightful presentation and
thank you.
Your thoughts.
Yeah, thank you, Dr. Mava.
I do hope that sessions will be considered and incorporated soon.
Yeah.
Right. Thank you. Thank you very much.
Thank you. Thank you, Dr.
Thank you all.
Thank you, everybody. Thanks.
Thank you very much. It was wonderful.
So, thank
Very
you.
nice.
Thank you.